Today, I'm going to talk about various methods of evaluation of tunnel liners. Essentially new methods, new high-speed methods of evaluating tunnel liners. And what I'm going to be talking about is ground-penetrating radar, infrared thermography, and high-resolution imaging. Talking about the methods, a little bit of the background, some of the theory, and then we're going to get into an example of how they're used in actual tunnels. So I think most of the people here, we're all bridge people, so we know what the problems with bridge decks, but tunnels are kind of a challenge. It's really an interesting situation with tunnels and evaluation of tunnel liners. Tunnels basically are quite difficult to evaluate. Tunnels are, as I list here, are in the constant presence of moisture, and over the time can experience deterioration of liners, corrosion of reinforcing steel and voids, and water flow through the liner. So the evaluation and maintenance is difficult, mainly because you do have limited access to the tunnel. Typically they're under high usage, they're accessible from one side only, and the presence of tile and so forth can make it difficult to actually evaluate the condition of the liner itself. So not to mention the fact that many tunnels are many feet in diameter, getting access to them is very, very difficult. So, you know, some tunnels are 20, 30 feet in diameter. So in order to get in there, you have to go in with a bucket truck, and typically that's very labor intensive. So there are manual methods that are available, as we all know, but they tend to be very labor intensive. Oftentimes require, well, most of the time require closures, and they tend to be expensive. So what's really needed is a more cost-effective method for doing this, for inspecting tunnel liners. Penetradar Corporation is one of the early companies involved in NDT on bridge decks and roadways with GPR. We're a manufacturer of ground-penetrating radar systems. We're a systems developer of IRT systems, HRI systems, which is imaging systems. And also we have vehicle inspection systems out. We're also involved in some R&D. Sharp, we have been involved with NASA and the NVESD guys out in Fort Belvoir. Those are the guys who do the mine detection, inspections and so forth, and development of systems. So we have about 100 vehicle systems out right now throughout the world, and we do have some systems with the military for landmine detection and IED detection. So in addition to that, we're also involved in consulting testing. We have a technical services group that does testing on bridges, roadways, and so forth, various types of geotechnical inspections. So now with regard to tunnel evaluation, I'm going to talk about some of the work that was done with under Sharp, RO6G, work under Sharp that investigated the use of NDT for tunnel evaluation, tunnel liner evaluation. As I said before, the tunnel liner evaluation is really a difficult thing, and so Sharp recognized that, and they identified this area of interest. And what they did is they actually, it was a project I think that Texas A&M was involved in, and they evaluated various technologies that are out there, and they determined that there are many technologies that are applicable. They ranked ground-penetrating radar quite high, infrared thermography, and several others. But I'm going to talk about the GPR, the IRT, and imaging for this. Before we get into the tunnel thing here, we're going to talk a little bit about these methods and where they came from, a little bit of background on them. Thermography is really a measurement of thermal characteristics on a structure. It's really measuring thermal differential or thermal gradients. It's been used for many different applications. Here we're showing how it's being used on bridge decks. Many of you, I'm sure, are familiar with infrared thermography to some degree, maybe on bridge deck evaluation. But it typically shows what a high-speed thermographic system looks like nowadays. It's installed on a vehicle, scans down a roadway, and it essentially paints a scan through a whole lane of pavement. Now, the history in thermography actually goes back to many, many years ago with the military. And the military is involved in many developments. In this case here, they were interested in identifying, you know, the thermal characteristics of jet aircraft and missiles and so forth. So they put a lot of effort into this type of technology. And now we're using it today for evaluating bridges and roadways, tunnels, and so forth. In the upper right, we have the test vehicle showing, a graphic of showing how it would evaluate a bridge deck. And then down in the lower section of the slide, we're showing an actual thermograph from a bridge deck itself. And I think it's pretty compelling. You can see all the features of the bridge deck, the curbs, the lane lines, the abutments. The patches are shown as blue patches, blue areas. And then, of course, the laminations are those red spots that you see scattered around. Now, this is on an asphalt-covered deck. Infrared is a fairly good method, a fairly good method for evaluation of bridge decks, especially exposed concrete decks. I guess, I think most people may be familiar with this to some degree, but thermography works on the principle of unequal heating. And in the case of a bridge deck, essentially the laminations are heating faster than the surrounding deck, and that's why they are detectable by thermography. And going on to ground penetrating radar, again, a little history on ground penetrating radar. It was actually developed, again, by the military. The type used for bridge deck evaluation, roadway evaluation for high speed was really identified for or developed for landmine detection. This goes back to the Vietnam War era. So the type that's used on bridges and roadways today use non-contacting antennas, meaning that they don't contact the ground, obviously. And of course, in the case of the military application where you're detecting landmines, well, obviously you don't want to touch the ground. So that was the idea there. The other type of GPR, which you may be familiar with, uses contacting antennas. And those were also developed for military applications, but not for landmines, but for rather detection of tunnels in Vietnam. So again, the military put a lot of effort into developing these techniques and methodologies, and of course we're using it today again to inspect bridges and roadways and tunnels. So GPR is very similar to, I shouldn't say similar, but kind of analogous to acoustic sounding in a way, only at a much higher frequency. GPR operates in the gigahertz range. Typically bridge decks and roadways are inspected with an antenna array, 3 to 4 antennas, and it's essentially one vehicle pass per lane. And then each scan is individually analyzed and assembled into a map, which is shown down below. And this is a map of a bridge deck on the bottom there, showing probability of delamination. And the red areas are the highest, and yellow and green and so forth. HRI, or high-resolution imaging. It's possible nowadays to collect very, very high-resolution images on bridges and roadways and tunnels. Now what's used are 4K cameras, and with that you can get very, very high resolution, very high scan rate. So at this high scan rate you can travel at 40, 50, 60 miles an hour. And what we're showing here in these images on the pictures on the side is a forward view from this imaging system, and then of course it's converted to a plan view, a downward view, which shows everything in its proper perspective. A little historical perspective on this also, that back in the day, some of the systems that did this were hundreds of thousands of dollars. And of course it took many people evaluating and developing high-speed film and splicing stuff together to get images. Nowadays we can do this for $1,000. So you can see the technology's advanced. What are the advantages of these NDT methods? As I've listed here, non-destructive, non-contacting, fast. Of course, in the tunnel world, 10 to 15 miles an hour is fast. And not affected by surface materials. I'm talking about GPR primarily. And how are they used? Well, many different things. Liner thickness, depth of reinforcing steel, delamination of concrete liner, could be debonding of shotcrete also, voids beneath the liner in the base, and water flow through the liner, and detection of cracks. So I'm going to talk a little bit about theory. This is where everybody gets kind of glassy-eyed and kind of the basic principles behind GPR and infrared thermography. This is actually a cross-sectional view of a GPR system. The upper left, you have a transmitter which transmits a monocycle. The monocycle is coupled through the antenna. It's emitted from the antenna, and you get a reflection and a transmission at every boundary. So you have air to asphalt. This is an asphalt, concrete, and base material. It could be a bridge deck or it could be a tunnel liner for that matter, but the principles are the same. You have a transmission and a reflection from each boundary, each electrical boundary, similar to material boundaries, but we're talking about electrical properties. So you have a reflection and a transmission. What we see are the reflections. We don't see the transmissions through the boundary. What's shown is a surface echo, and then from the next layer down, we get a reflection from the asphalt concrete echo, or from the asphalt concrete interface, and then one from the bottom of the concrete. And these appear in time relative to the thickness of the material. And so what we can do is we can actually look at the radar waveform in an analytical sense, and we can, based on the magnitude and the phase and the time separation between these echoes, these individual echoes, we can determine everything about the material that we need to know in a theoretical sense. Of course, there are some practical issues related to that, but in theory, you can do all that. So the GPR system provides all that information. Now, getting into tunnel liner thickness, what do we do with, how do we analyze tunnel liners? Well, measuring thickness, going back to your Physics 101, distance or thickness equals velocity times time. And essentially what we do is we're measuring the time separation between echoes, and knowing the velocity through that material, we can determine thickness, x equals vt. Voids, voids, let's say an air void has a very characteristic type effect on the radar signal. Essentially what you're doing is going from a concrete or some type of solid material to an air gap beneath it. And that shows up as a very significant reflection. You can see in this echo C, I should say. That would be the characteristic reflection from a void. So when we're evaluating tunnel liners, or it could be pavements for that matter, we see that characteristic type signal when a void is present, so that's how we detect voids. Water saturated base, the same thing. We're looking for that type of reflection from behind the base material, except in this case it's inverted in phase, and it tends to be quite large based on the reflection coefficient from that material. So in the case of water saturated materials, we actually measure the reflection coefficient or the refractive index, and that's really determined by the dielectric constant of the material. I don't want to get into the weeds with the technical aspects, but essentially that's what we're doing. It's a measurement of the radar properties. Now, concrete deterioration, a little bit different phenomenon. We're looking for actual loss of signal or attenuation in the material. Typically, in a deteriorated concrete liner, it could be a concrete tunnel liner, it could be a bridge deck. But typically, those deteriorated concrete areas will hold moisture, oftentimes chlorides, and they tend to attenuate the signal quite significantly. And essentially what happens is it more or less flattens out the radar signal. It attenuates the radar signal. And by measuring this attenuation, we can identify areas of deterioration. And this is one of the things that actually goes way back to the Sharp 1 days, where we identified that as one of the primary discriminants in detecting bridge deck deterioration. Concrete deterioration is actually using that principle of the intrusion of chlorides and moisture into the concrete and identifying those locations to accurately identify deterioration of concrete decks. So we're using the same principle here in concrete or in tunnel liners. Now, infrared thermography, entirely different concept, different principle. The two methods are pretty much mutually independent. Thermography is really based on temperature differentials, as I said before. It's really based on differences in the thermal characteristics, which cause differences in temperatures at the surface of the material. Thermography doesn't give you information about the inside of the material only, but it does in as much as the fact that if you have conduction to the surface, you can measure that temperature gradient. One thing is, even though you are measuring temperature differences, you have to keep in mind too that different materials have different emissivities, and the different emissivity can give you a different temperature result, even though there may be no physical change in the material outside of the fact that it may be a different color. Dark materials will absorb and radiate differently than lighter colors, so that's one kind of an anomalous situation when you're utilizing infrared thermography. But clearly, what we do know is that moisture, deterioration, cracking, and so forth will conduct heat differently than sound concrete. So we utilize that principle when we're evaluating tunnel liners. And that, again, holds true for bridge decks as well. Now, the method that we utilize for tunnel evaluation is a little bit, well, maybe a little unusual. It kind of follows along the way we do bridge deck evaluations with GPR, that is. We're making several scans, longitudinal scans along the length of the structure, except instead of looking down along a deck and traveling straight forward along the length of the structure, we're actually positioning the antenna against the tunnel wall, as you see in this graphic here. And we position the antenna in every clock position, typically 2 to 3 feet spaced apart, and make longitudinal passes along the length of the tunnel. Again, you know, from a tunnel standpoint, it's fairly fast. We're traveling 10 to 15 miles an hour. Compared to manual inspections, it is somewhat rapid. Now, with infrared and the imaging, we're making 2 or 3 scans. The coverage is significantly greater than the GPR coverage. So only 2 or 3 scans are necessary to cover the entire inside of the tunnel. Now, what I'm showing here is a configuration that we developed for tunnel evaluation. It's showing a GPR vehicle, and then we built a structure that goes on the front of this vehicle. And what it does is it positions the antenna right up against the tunnel liner. And with this, we can actually move the antenna in and out. So obviously, it doesn't hit any of the appurtenances or anything like that. But in a case like that, we're able to scan fairly efficiently the tunnel liners. It's also been used on rail tunnels on a high rail vehicle. So you can see this one here is, I think, in the Dallas Start tunnel. Something we did for the RO6G project. There are 2 tunnels in Pittsburgh. This is part of the implementation project for the RO6G. And this kind of gives you a kind of a real-world flavor of what these technologies can do. This is the Liberty Tunnel and the Armstrong Tunnel, a couple of fairly old tunnels. The Liberty is about over a mile long, and the Armstrong is about 1,000 feet, built in the 20s and 30s. The Liberty had just been rehabbed. In other words, they put in a shotcrete overlay liner, and of course the Armstrong was a mess. It was in pretty rough shape. But we did the testing, and using GPR and infrared thermography and the imaging. So in the Liberty Tunnel, essentially what we were doing was we used the 3 methods. The idea there with GPR was to detect the laminations, deterioration, voids, high moisture, areas of moisture in the liner and behind the liner. And then the infrared, as I said before, was used for detection of water flow and surface moisture, cracks, debonded tiles. And then, of course, we used the HRI to correlate with those NDT methods. And then, again, just to summarize, again, not getting into too much detail, but just to give you an idea of what these methods can do. With the Liberty Tunnel, that's the mile-long tunnel, about 177,000 square feet of liner inspected in one evening. It's over a mile in length. And again, these are some of the results we got. GPR detected 4.1% of the area. 4.1% of the area inspected was deteriorated, which is not too much. But when comparing to some of the test areas, we had some ground truth test areas. The GPR detected pretty much what the sounding, we use sounding to correlate. And GPR measured or detected pretty much what the sounding detected, 11.9% for GPR, 7.2. GPR tends to detect a little bit more than sounding for various reasons, but when you compare the two, the GPR detected 73% of the areas detected by sounding, which were delaminated, and also detected 90% of the good areas. So it's not too bad. And water-filled voids, GPR detected 13%, air-filled voids 6%. Unfortunately, with this tunnel, and this is a kind of interesting point, the infrared really did not result or yield anything of any, well, not very usable. And we believe that in long tunnels, infrared is not really that effective, mainly because you need to have a thermal gradient. Typically on bridge decks, for instance, you have the solar heating, which heats the delamination or deteriorated areas, debonded areas. In a long tunnel, you have none of that. So you may have some very slight temperature gradients, but again, you know, thermal cameras are about 1/10 of a degree, maybe 0.04 degrees at best. And I think that some of the temperature gradients, temperature differentials are even less than that, if at all. So for long tunnels, we really don't recommend the IRT, but GPR did produce some pretty compelling results. I want to say too that with what we were detecting with the GPR was kind of interesting. We weren't really seeing delamination. There was no reinforcing steel in the liner, but there was, what we did detect was debonding of the shotcrete. And this is kind of interesting because the shotcrete was only about 1.5 inches thick. And what we were actually seeing was the fracture or the separation between the shotcrete and the base material. And of course, what we use for that is a kind of a signal processing method that we developed called decorrelation, where we do some fancy signal processing to subtract out signals to enhance the detection. But that worked out quite well. So again, what we're finding is that with bridge decks, we know quite a bit. We know how to deal with them. We know the structures. Tunnels, it's kind of a new thing, and we're finding that the analysis methods that you use really need to be tailored to the specific structure of the tunnel, the type of rehabilitation that's been done on it. And it takes a little bit of understanding of you know, GPR, infrared thermography, and the physical environment as well to effectively utilize these methods. Now, the Armstrong is a little bit different. It did not have a shotcrete liner, but it was in fairly poor shape, I would say. What we did find is concrete deterioration. And what we used for that method there, what we used for detection of the deterioration in that liner was what we use for bridge decks, and that follows the ASTM DO 6087 standard. We're looking for attenuation in the material. So essentially, we found medium or high attenuation, about 14% of the wall area. Moisture is also detected, high moisture in about 14.1%, about 10+% moisture detected in 14.1%, and lesser moisture in the remaining part of the liner. So GPR was effective in detecting moisture, and it was effective in detecting deteriorated concrete. Of course, from these tunnels, we had thousands of feet of data. I'm just showing maybe 100 feet or so. But on the top here, we have a high-resolution image, infrared thermal image, second, GPR attenuation, showing the loss or the attenuation in the liner. And then at the bottom, we show the GPR measurement of dielectric constant, which is really a measurement of the moisture content in the material. Just taking a couple spots along the way, and this is how we kind of identify these areas of deterioration. If you look at distance 42 feet, if you look at the HRI, the image at the top, it really looks clean. There's really no visible flaw. There was that's the Armstrong tunnel, and there was a tile liner in the bottom half of that. So you see in the tile liner, there's really no visible problem. With the infrared thermography, you do see a cold spot at 42 feet. No attenuation, but you do also see a low dielectric constant. So that tells us right there that you've got a debonded tile. So in the Armstrong tunnel, we were able to see debonding of the tiles based on those principles there. And then going to 80 feet, there was a missing tile there. We see no temperature variation whatsoever, but we do see relatively high attenuation. So we're identifying that as a deteriorated area. And then going on to 100 feet, we're essentially seeing the same thing. Missing tile, high attenuation, essentially an area of deterioration. I'm not going to get into this, but this is more data that we collected and evaluated from the tunnels. That was showing the east and west wall statistics on attenuation, and then the same thing with dielectric constant, showing the differences between the east and west walls of these tunnels, and the thermal differences and so forth. But I guess I want to conclude now. What we found in our work with the RO6G implementation project was that these methods, these NDT methods, were feasible in practice. And what we showed here was that we were able to identify equipment specs, procedures. We demonstrated, developed and demonstrated procedures for collecting data and methods for analyzing data. So one point I wanted to make, maybe emphasize again, is that the methods of analysis are tunnel specific. So methods of analysis are tunnel specific, and our thought is that the combination of technology should be used. There is merit in using all three of those technologies. Overall, good correspondence between the NDT and ground truth, and going forward, I think what we need to do is use the methods and then finally develop some standards, which is what typically would happen, but those are our recommendations at that point. And I guess one other thing I want to say, there is you know, some of the questions I've had for the costs are, just to give you an idea, it's kind of a rough ballpark figure, for those tunnels, roughly about $30,000 per the long tunnel per test method. So it's really, from the standpoint of providing that quantity of information, I think it's, in my opinion, it's fairly cost effective.
I understand when you used infrared in the tunnels and you didn't get much useful data. I would say I'd be very surprised if you actually get very useful data in a tunnel with an infrared. I mean, we've had a hell of a time on bridge decks with the sun shining on it. You know the problem we had in Hawaii. Every time it rained, we just lost everything. So would you still recommend that infrared be tried in tunnels? Would you actually detect a water leak would create such a differential for it?
Well, yeah, I think that, well, let me just put it this way. The utility of infrared is less than GPR and maybe less than the imaging. I think the imaging is important because it gives you the opportunity to correlate what's on the surface and what you see behind the surface. Although I wouldn't discount infrared because it is an effective tool. It is useful in many cases. As I said, we would not recommend using it in a long tunnel, even though you may be able to identify water flow. Now, in the one case with the Liberty Tunnel, which is the mile-long tunnel, we did not see any water flow, and visibly we did not see any water flow. So really, it wasn't a good test for the infrared in that case. But in the Armstrong Tunnel, which is the shorter one, it's about 1,000 feet long, we did see that. So it has use, it has utility in those areas, but again, you have to know when to apply the technologies. You shouldn't, out of hand just dismiss one technology because it may not work in one situation, but you have to know when to use it and how to use it and what it's going to provide. So I don't know if that answers the question, but that's what we would do. Okay, all right, thanks.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.